So my title well, I changed my title, as you can see, because the question that was asked is talk broadly about science, but honestly, I want to talk about how quantum science needs mathematicians. And I can say that in many different ways, because there is actually people in the room here that can attest that I need mathematicians. I'm a computational chemist by training. I got into quantum 10 years ago. Before that, I spent 15 years doing HPC. My group also does a little bit of AI on the side. The same reason, I need quantum technology so I can solve my science problems. Early on, I realized I needed computer scientists and applied mathematicians. So they have been part of my journey and my projects since I started in quantum. So this had to be very high level, so I'm making it very high level. And maybe a little bit too basic for some, but I think we want to get everybody on the same page. One of the things you have to realize, quantum is already there. So we talk about a quantum revolution, we're actually talking about a second quantum revolution. Quantum is everywhere. MRI, light. You don't realize it, but your lights are working because we have quantum mechanics. But also, the building of transistors is fundamentally a quantum process. So quantum is there already, every day. But we want to take quantum to the next level, and that's where a lot of the efforts have been in the last, I would say, 10 years. So to give you a little bit of the primer of the basics of what makes quantum quantum, these are the basic ingredients. Superposition, measurement, interference. We actually use the signal processing, interference processes, to do quantum algorithms. But most importantly, entanglement. That really is what makes quantum quantum. And honestly, the rest is just math. A lot of it is linear algebra. So I'll go through some of these concepts a little bit to make sure that everybody is on the same page. So first of all, superposition. Everybody, if they have heard the story about superposition, they've heard about Schrödinger's cat. Effectively, is the cat dead or alive? It's either, as long as you don't measure. But the key part here, once you measure, it is either dead or alive. It won't be both. So measurement impacts the outcome of what you're seeing. How you measure, and I can't really represent this in an easy way, or which basis for a mathematician determines if you get information or gibberish. So if I encode it in a certain way, I want to read it out in a certain way. If I read it in a very different way, I just get a random number. The third concept related to measurement is that you cannot copy the quantum information. Again, if I give you a piece of quantum information, you don't know how it is encoded. And because you don't know how it's encoded, you could get anything, a random number. So it doesn't help you. Now, of course, there is a lot of stories around Einstein being not very happy with these kind of things. He really did not like the concept of chance, randomness. Bohr had a very different opinion of that, as you can see on the left. By the way, that's me on the right. I actually visited earlier this year Niels Bohr's office in Copenhagen. So if you ever get a chance to go to the Niels Bohr Institute, they will take you around. Everything is original. So it's very cool to sit at the table that made history. So it's not just a theoretical concept that we have superposition. It actually has been proven, right? Two-slit experiment is on the left. But what's really interesting to me is that they're trying to figure out where quantum ends, in the sense of how big do you have to go before quantum doesn't really show up anymore. So they now have done these kind of two-slit experiments with these big biomolecules. They still see quantum interference processes. So they still see superposition and uncertainty. Now they have to go bigger and bigger, and we don't live as people in a superposition, right? So there is some range where that stops to become actually a real process happening. So the other process that is really that really makes quantum powerful is entanglement. Again, Einstein did not like all of these uncertainties, so that's why he talked about spooky action at a distance. What that really, entanglement really drives to is that we have information that is globally accessible. And I'll give you that in a slightly different way. So let's say you have two qubits or two pieces, two entities that have some quantum information. They are entangled. So entanglement means they have to be very close. They have to be able to interact with each other to get entangled. But if you then place them far away, and I've seen these in very different ways. Actually, I was watching Preskill's talk from the Wolfgang Pauli lecture earlier this year. And so this is kind of based on how he has said it. You spread the information out. You have now two pieces that are far away. They could not communicate at the speed of light or anything. And what you now have is two independent qubits, for example. And you could measure them, but you get a random piece of information. It could be either of these quantum books, right? The other side could do the same thing. They can measure, and they could get either of these pieces of information. There is no way they could determine which piece of information they get. What's interesting about entanglement is that if I measure the information in a certain way, and the other person far away measures the same way the information, we'll get the same answer. What that means is that the information that is stored in qubits is non-local. It's stored in what they call the quantum correlations. So what that means effectively is I don't have local information on this side. I don't know all the answers on what I have as information on this side or on that side. I only have the information if we all measure collectively and get the information globally. And this is effectively what is done in a lot of ways, the same when you have lots of qubits. So classically, if you read a book, you read one page at a time. And once you've read all the pages, you've read the whole book and you know what you're talking about. This is not how it works in quantum. You cannot read each qubit and then know what the information is. You actually have to read them all at once to get all the information. So you read it once, and now you have the information that was there. And I like this book. This is, in a lot of ways, especially in the Berkeley world, considered the Bible when it comes to quantum computing. So it's a collective measurement that you have to do. You have to measure them all at the same time, and then you can actually reveal the information in a qubit. And by the way, this is also the approach that drives, for example, error correction, which I'll get to in a little bit. Okay, so again, Einstein does not like this. Schrödinger actually wrote something interesting. It says, it's interesting that you get the information about the global system, but you cannot get information locally. And so he talked about that in this paper a while ago. Okay, so what's the new revolution then? You have quantum everywhere. So the next revolution is really in three areas. Quantum computing, so next level simulations, quantum networking, moving data securely, and that's really the driving force, moving data securely. If anybody ever tells you we're going to move data faster than we can do classically, it's not going to happen. It can never go faster than the speed of light. And then the third one is quantum sensors. And that can be done from materials all the way to gravitational waves. I won't talk too much about the last two. There will be some talks about networking, I know that for sure. I would say that the two on the right, networks and sensors, are more of an engineering problem by now. They fundamentally use the entanglement and concept to get to more accurate sensors, faster, secure communication. I think the most room for applied mathematicians is in quantum computing. So we saw this already earlier. Feynman really proposed that idea in 1982, where he said, well, we're way better off using quantum systems to solve quantum problems. You can't do it efficiently on a classical computer. So that's fine. He posed that as a long-time solution a long time ago. And not much happened till, I think, Shor came up with his actual factorization algorithm. The change towards, hey, you can actually do an algorithm on a quantum computer changed a lot of things. Now, this is not his first paper on this topic, but I thought it would be nice to show you this paper. As it says on the bottom, this was published in SIAM. So it is math, and it is of interest to mathematicians. So why are quantum computers so good for quantum computing? It's the amount of information they can store. So you can store 2 to the n complex numbers in a state that is multiple qubits. So 100 qubits, good qubits, is 2 to the 100 states. Well, you can do your math very quickly. I can't, because that's a lot of zeros, but it quickly reaches the number of particles in the universe. So the potential power of the information you can store in a quantum computer is large. The hard part is how you then operate on it. So for us, so I'm part of the Department of Energy National Lab, Lawrence Berkeley Lab. We really are driven by how we can use quantum computing to accelerate discovery science. So for us, I would say the most important things are algorithmic speedups over classical computing. Quantum simulation is a very important aspect. We do a lot of work on optimization algorithms, and the one thing we do not work on is unbreakable encryption protocols. I should say our lab probably doesn't. There is some certain national security labs that might have some interest in that. But that is not a science problem that the Department of Energy is interested in. To give you briefly some examples, so for me, I'm a computational chemist. I'm really into trying to find better ways to do molecular sciences on quantum computers. So everybody that has ever opened a book or read an article, they're always throwing out the FOMOCO molecule as a way to argue that quantum computers are going to revolutionize chemistry. I would say that is a very simplistic view of the world because it's a lot more complicated than simply doing ground state energy. I think the real interesting part is in dynamics of these kinds of systems, such as what happens when a catalyst reacts with water induced by photons or by solar light. A lot of these simulations cannot be done classically on the scale or the type that we would like to. We believe you could do this by the 100 or 200 ideal qubits, good qubits, which we are not at right now. But again, that's the information scale that we want to be able to reach. I can go the same with material science. We still have a lot of issues understanding superconductivity. These are very hard to compute. That also holds for battery materials. Understanding the physics of battery materials is hard to model these days. But it's not just chemistry or materials, it is physics too. So understanding the fundamental building blocks of nature, there is an enormous amount of work that has to be done. Everything is driven by experiments right now, but the simulation capability that's needed to even understand the physics parts is something that is very hard to do on classical computers. So I wanted to give you one side note here. Speed up might not be the only factor when it could be a quantum advantage. Sure, we could solve larger problems faster, potentially, but there is no guarantee. We do not have shown in algorithmic ways on quantum computers that we can get through quantum advantage. But there is a potential that quantum computers could be lower in energy, cheaper. Hey, well, just look at the numbers for Frontier. They're huge, right? If you can get the kilowatts, I think there would be a lot of happiness around these kinds of systems. Well, that's not completely realistic, but at least if we can get a couple of orders of magnitude less power, there's a good reason for that to happen. If they're cheaper, every university can have one. Just imagine a computer at that scale at a university and how that could impact science. Okay, so quantum computers come in many flavors. There were mentioned already some of them. I would say atoms, ions, and superconducting kind of are the leading platforms at this point in time. I would say for the longest time, superconducting was the leading platform. I would say they are really being challenged right now by ions and especially atoms. My quantum center has been focusing a lot on atoms and ions, and actually one of the newest companies, Quera, that does cold atoms, actually is built based on a lot of the technologies that came out of a center. But there's a lot of other things that one could go for. Solid-state spins, Majoranas is something that is very elusive, and many people have searched for it. But there's also work to do photons. You could just do photons and interference patterns and actually encode your quantum information into photonic systems. And then you have electrons, which is a couple of parts of the ecosystem are really focusing on electrons above surfaces, for example. Okay, so we have lots of different flavors. So where are we at when it comes to quantum computers, quantum systems? They're getting better, I should say. And as I said, we cannot get the right level of computing right now that we would like to really solve scientific problems. But we're getting better. They're getting higher and higher gate fidelities. Now, realize this is the best gate fidelity, 99.9. Think of your classical computer. It's a very different story, right? But this is a big progress of where things were a couple of years ago. We were not even at 99. We were at 98, 97. So there's a lot of progress that has been made across the spectrum of technologies to really move this forward, which is actually what's exciting about it from a physics point of view. They have lots of different technologies that effectively are learning from each other, but also kind of competing a little bit with each other. So we're getting better at having accurate computers, but we're also starting to get to use quantum computers in a different way. So we're thinking about how we can use quantum computers in new ways. So here are some examples. They're doing new types of 2-qubit gates. So 2-qubit gates are the entangling gates, which really allow us to have the power on quantum computers. There's things where they are not just doing 2, but many qubits. We can do things now in parallel. We can actually use more levels. And when we say qubits, we're going 0 or 1. Well, you can actually go 0, 1, 2, or 0, 1, 2, 3, 4. Just imagine now it's not 2 to the n, but it's 3 to the n, 4 to the n. So your information grows even quicker with fewer of those qubits, as they call them. Another big progress that has happened really in the last year or so is mid-circuit measurement, which allows us to do a lot more things, like actually starting to think about error correction to fix some of our problems. So again, this happens across all of these technologies because they are realizing when they're starting to develop algorithms that they need these features. And this is an opportunity for the people developing algorithms to really inform the physics development of hardware as to what features would help actually be efficient, delivering efficient algorithms on quantum computers. So the number of qubits is also growing. You've seen probably some of these highlights come through. So IBM actually has a bigger one than 133. They have in the order 400 on a chip. But the neutral atom people are getting into thousands. So they're growing systems at the same time. I would say IBM also is trying to couple multiple systems to grow them. So there's a lot of challenges that come with this, though, because if I have large systems, and I just told you that 100 qubits is 2 to the 100 piece of information, I can't store that on a classical computer anymore. So how do you know if your quantum algorithm works, if your quantum computer is doing the right thing? It's hard to simulate that at this point in time. And then validate the results. So here's a new angle that people have been working on, tensor networks, because they have seen that in certain cases, in certain types of problems, they can actually simulate larger systems effectively in an approximate way and really do this kind of validation of hardware platforms. And if you're worried that this is an area that you should go into or your students should go into, it's a sprawling industry. And this is not the newest graph that is out there. There is a large number of companies that go from hardware to software to algorithms and everything in between. The ecosystem that quantum is huge. And then you have also a lot of end-user companies that have people internally to try and understand where the opportunities are for quantum in the future when they are actually going to use them. Now that's industry, but I cannot be complete if I don't talk about some of the centers that have been formed and have been running for the last 4 years. So NSF has done this, but I'll focus primarily on the Department of Energy. So they started 4 years ago, 5 National Quantum Initiative Centers. So I took over half a year ago the Quantum System Accelerator, which is about 400 people that are distributed over 3 national labs and 12 universities. But the key part is we're trying to solve big challenges through integrated teams. And there is mathematicians in there too. Mathematicians, computer scientists. This is not just physicists that are able to do these kind of things. And we've moved the needle when we do these kinds of experiments. We really have moved 2 qubit fidelities from 99.5 to, that should be 99.9 actually by now. We've gone from doing almost nothing to being able to run large systems and actually do real science with it. The systems that we have at the order of 200, 300 atoms, actually you can do real science with them. And we have a lot of different, especially material science and physics papers that are showing that these systems, even though they're noisy, can do a lot of things. Now that sounds all rosy, but they're not there yet. There's still a lot of challenges to make useful quantum computers. I would say we're getting close. Well, I kind of just said so. We almost have good enough qubits to do specialized quantum simulations or quantum applications. But our biggest problem is coherence. The available computing time is still short, and that's driven by noise and errors. Noise and errors in this case means I have stored quantum information into my system, and my environment is perturbing it to a point that I lose information. But there is also at that point the same thing, a lot of opportunities for algorithmic advances. Can we make more efficient algorithms that require fewer operations that allow us to actually do a lot of physics, a lot of science within the available compute time that a quantum computer has right now? So it's software tools, it's compilers that really are critical to make quantum computing broadly approachable, but also broadly accessible for the end-using community. Also, we need help designing better chips. Sure, we can do the experiments, we can design a chip and try to do that in the lab and see how it works. But there is a lot of work that still has to be done. Again, where applied math can be an important player. So when you look at it, where the field is, you see the hardware teams thinking about increasing the number of qubits, increasing lifetime and fidelity, and trying to find ways to reduce errors. While you also have the applied math and computer science community working on algorithms and software so they can use fewer qubits, decrease the number of operations, and incorporate error resilience in your algorithm. And mathematicians are needed here everywhere. And I'll stress that again on this one. Just look at the words that you can look at the bottom of different aspects of the quantum stack. Algorithms, software, programming tools, control protocols, which is optimization. Design, which is, think AMR, for example, to actually model these kinds of systems. Once you have prototypes, you need to control them, operate them. You need to do stats. You need to do analysis of the results that come off of it. I only hear math at that point in time. I'll give you a good example of design, right? This is adaptive measure refinements could be very useful to design things like, on the left, a trapped ion chip. You can see the delicacies and you have to do a lot of electromagnetic simulations to get this right. They are actually not using the tools. They are using a standard that is industry that is not good enough. You can look at the left, there is multiple. Gridium is one of that has come out of our center. This is the first time we have what's called a grid state qubit that actually has some topological protection, which topology is something that is very mathematical. So there's a lot of opportunities to think about how to make new qubits based on mathematical concepts that have internal protection. And there's many more that you can go through. So that's just designing chips. Optimization challenges are everywhere. On a widely used algorithm, variational quantum eigensolver, effectively is an optimizer. So we only measure on a quantum computer, the rest is done classically. So the optimization process that we have inherently is done classically. Key part, the information that comes out of a quantum computer is noisy. So does anybody have a very good algorithm to do noisy optimization? It's still a big challenge in the community to do this right. Other example, compiling. It's a synthesis problem, effectively. There's a lot of room to do algorithmic discovery, look at gate sets, understand how we can align it with hardware, but especially the last bullet, global circuit optimization. It's an NP-hard problem. It's very challenging. So what do? We do heuristics. There must be better ways to do this. So there's a lot of efforts that one could think of here in the optimization world. And again, it boils down to many opportunities to improve noisy optimization. Oh, darn, this one didn't show automatically. But so, this is a neutral atom system. They're doing parallel operations. We can make them more complex, multiple atoms moving around. That's a global optimization problem. And it becomes big if you do a lot of atoms. How do you do effectively a series of operations efficiently? Again, it's an optimization problem. Pulse shaping is something that Q-Control has done for a while to figure out how to reduce noise in the gates, but there is still a lot more work to do. And there is more of those on the bottom. So how do you actually do the operations, which are real photonic signals? How do you do those in the most optimal way to reduce the noise? Again, optimization. Now I can say that I personally had to rely on applied mathematicians. So we've been working on, this is some work actually doing variational quantum eigensolvers. But we took an approach that is not just variational quantum, but we took another approach on top of that to get some more information and then change the simulation effectively into something that looks like this eigenvalue problem. There's a big problem with this because the metric, as is the metric here, will be very noisy. Well, you cannot have that. So we actually worked, and Roel is sitting in the front here, with the applied mathematicians to really understand how we can take special care of our data to make sure that these eigensolvers are actually giving us a reasonable result. So again, we've had them, and I have had my partnerships with applied mathematicians for a long time. And while Roel's sitting here, I'll throw also the other one out there. It's like one of the hot topics right now is block encodings. It's a very challenging problem. You want to do non-unitary operations on a unitary system. That's hard. It's very hard. How do you do this efficiently? So my mathematician friends developed a code called Fable. to actually generate circuits, generate operations to do block encoding in an efficient way on a quantum computer. Again, there is a lot of concepts you can work on when it comes to being an applied mathematician. The other one that I wanted to briefly touch on is quantum subspace, building on top of the quantum subspace expansion. So we developed the concept of quantum subspace expansion, which is the generalized eigenvalue problem you just saw. But again, we brought in some applied mathematicians here to rethink the problem. Instead of doing it in the standard way that we can also change the basis and go into a real-time evolution in a unitary form. Turns out, now it has a tuplet structure, which means we only have to do a linear number of measurements instead of a quadratic, which is a good thing because now we have less sources of noise. But this also requires to think about how do you do your measurements over time? How do you spread them out? What is the impact on it when you do different time steps? And how does it impact grabbing enough of the information of the states that you want out of your spectrum? So that's a mathematical problem that really was solved this way. And I think this is a very successful algorithm out there right now. Okay. So the final topic I'll touch on is noise. It's quantum systems' biggest nemesis is noise. So any interaction between the quantum system, the qubits that you have, and its environment leads to either information loss or information scrambling. Now the hard part is we can actually build quantum systems that do not interact with the environment. It's great. They don't interact with the environment. But me, as a person operating a quantum computer, is the environment. So we can't use them. So this is the struggle we have in the field of quantum computing, is that we need to operate on them, we need to interact with our system, but we want to be able to control how we interact with these systems. And we don't want anybody else to interact with these systems. Now, quantum sensing is quite the opposite. They want the environment to interact, but they want the smallest piece of information, that the smallest interaction with the environment, to make sure that they can get the most sensitive sensor coming out of it. Okay, so we have noise. How do we deal with it? Well, quantum error correction is one way to do it. So how do we do it? Effectively the same concept that we went in reverse, we now do in a forward way. I have a book. I encode it non-locally in the correlations across many qubits. It's not different than, to some extent, it's not that different from a classical repetition code to begin error correction. The only difference is that as soon as I interact with one of these qubits, there is no way I can get information out of it because it's not stored on a qubit. It's stored in the correlations between these qubits. So as a result, the damage can be reversed. So you send our favorite fan Gilbert out, and the only way to then do the repair is do some carefully selected collective measurement of all the qubits in a way that you're not looking at the information, and then make a repair. So it can be done, but it's hard because you need to be very careful on how you do the measurements across many qubits, how to not reveal information, and only then fix the qubit that is broken. But again, the key part is we're doing it with non-local correlations, not by explicitly interacting with a qubit and getting information, because once you do that, you've just broken down your entanglement. So there's lots of codes that are out there. There's actually a lot more new codes that are being developed. The surface code is a well-known example. There is heavy hex, so some of the hardware is very well aligned. IBM recently put out the low-density parity code as a new concept. They all have the potential, with accurate enough hardware, as a long-term solution to build reliable quantum computers. The hard part is, the more noisy a quantum computer is, the more qubits I need to correct it. So it's still a competition of building more and more accurate qubits so that we need less and less of these entities, these bits, to do error correction. So it's, again, a balance between moving forward the hardware field and building error correction codes that are more and more efficient. And I think there is, from both directions, still opportunities to move that field forward. We did a little bit of this, so this is not correction, but actually we used detection and then throwing away what doesn't work, something that's called the 422 code. You can solve this problem in 2 qubits. Well, really, if you really want to go, you can actually solve it in 1 qubit. But by doing this, actually putting some error correction in there and detecting the error and not correcting it, so throwing away the bad stuff, we can actually get very close for a very small problem very accurately. This is very small. This is not the problems we would like to run in the long run, but it was a good demonstration at the time. Now things have changed. There is a lot more demonstrations of error correction. We've now seen the first results where you have error correction being slightly better than non-error corrected. Now keep that in mind, slightly better than non-error corrected. It's not said it gives you a perfect answer. So that balance is still there because the quantum computers are still so noisy and we do not have enough qubits out there right now on a quantum computer. We simply cannot build the error correction codes to get to the reliability that we need. But there is a lot of efforts in many different directions to move this field forward. So from a hardware point of view, we're moving that way. I think there's still a lot of opportunities on the error correction codes on the math side to move things forward too. In my last couple of minutes, I want to throw 2 other things out there just to think about. So we need to be able to validate our quantum computers. How to do that is very challenging. So this is a concept that was developed really at Sandia as part of one of my earlier programs, where they developed a concept called mirror circuits. There's lots of ways you could do this. You could do your operations forward, you can do your operations back, and you can look at where you started and where you ended and see how well you did. But a lot of these concepts are needed to really get a sense of how good a quantum computer is, or is it actually doing the right thing? So new ways of actually doing efficient validation, new mathematical concepts to do efficient validation are still, I think, an area to go and build upon compared to where we are. The other thing, as I mentioned, our quantum computers are getting bigger, but the real problems we just want to solve probably are still beyond the size of a single quantum computer. Now, quantum networking is our hope that because we cannot build quantum computers just bigger and bigger and bigger, physics-wise, we cannot put more qubits in a single device indiscriminately. So we need to connect them, like a classical computer, network them. Networking is a growing field now, I would say, but the amount of people working on how to couple quantum computers within that field is still a little bit more narrow. So one approach that has been developed at multiple institutions is literally break the problem up in smaller pieces. But that is not that trivial to do. If you really think about it, if I have a system that is fully entangled and I break it up in pieces, do the compute, and now I have to reassemble the information classically, that's still going to be an NP-hard problem in the long run because you have to do all the correlations again. So these approaches work when you have sparsity, so that some pieces are interacting with each other and some others are, but the 2 pieces are not really interacting together. So the stitching together is actually what the hard part is. And that's, again, a mathematical problem that I think there's still room to advance that field. Okay, and I'll close with this slide. one of the things that I have been trying to get across too is that, sure, the race to the moon was great, but the race to the moon really delivered many ancillary technologies. And I think the quantum field, the algorithmic field, the mathematical field can make a lot of progress. So you see quantum-inspired algorithms already speeding up classical computing. A great example is Google's quantum supremacy experiment that used to take many, many years to compute. It now can be done on a laptop because the mathematicians figured out how to do it smartly. There's a lot of novel quantum hardware technologies that could find their way in classical computing. So even when you're working on classical computing, you should start thinking about what part of a quantum system could be useful in your system, in a classical computing sense, algorithmically. And honestly, for us still, quantum physics is still a big challenge. If anybody claims to you they understand quantum physics, then they're lying. I don't understand it still. It's still a very interesting concept, and even the experimentalists have not been able to fully grasp it from their experiments. They're still designing new ways to probe this concept. But effectively, understanding the concepts allows us to figure out how we can do classical computing better. So I would say, even though we don't have a fully operational quantum computer, there is a lot of progress that has been made to allow us to actually do things that we could not do before this started. So I hope that I convinced you in this talk that quantum is not too scary and math is important. So if you have anything you wanted to talk about or with me, or you want to work on collaborations, we love to work with mathematicians and computer scientists. Come talk to me. And that's what I have for today.